Hello friends, welcome back to NPTEL online certification course on soil and water conservation engineering. I am Rajendra Singh, professor in agriculture and food engineering department of IIT Kharagpur. We are in week 6, lecture 29, and the topic today is basics of open channel hydraulics part 1. To have a relook at the course content of this week, we started this week with lecture 26, introducing the gully control measures. We continued in lecture 27 with gully control measures and with a special focus on permanent structures. And then lecture 28 was on design considerations for permanent gully control structures. And this lecture will be basics of open channel hydraulics part 1, and the basics of open channel hydraulics will continue in lecture 30. That will be the next lecture, that will be part 2. Now, coming to open channels, it's a open channel is a conduit where liquid flows with a free surface and free surface is in contact with atmosphere. So, we know that every time we draw a trapezoidal channel, and then we make a water surface, and then we put the dimensions. So, that simply means it is a liquid flows with a free surface and the pressure on the liquid surface is atmospheric. And the different examples of open channel could be rivers, they are the greatest examples, then streams, irrigation canals, storm drains, street gutters, and sewers that are flowing partially full. For example, this one, this is also example of open channel. And open channels could have different cross sectional shapes. For example, we have already seen trapezoidal, triangular, rectangular, and also as we have seen that it could be circular conduit flowing partially full, that could be example of sewer. So, this could also be a particular shape. So, these are various possible shapes of open channels. Then coming to the flow classification, based on fluid particle motion, flow is basically classified into two categories, laminar flow and turbulent flow. So, basically say fluid particle motion, we know that if it is laminar flow, the flow there will follow streamlines, and whereas in turbulent motion streamlines will not be followed. And typically this classification is based on Reynolds number, that is designated by R suffix E and given by rho V d by mu or V d by nu. So, this is the formula which we used for finding out Reynolds number. And for open channel flow, and especially the flow to be laminar, Reynolds number should be less than 500. And for turbulent flow, Reynolds number will be greater than 500. I am sure that you must have read in hydraulics pipe flow, and in pipe flow laminar flow limit was Reynolds number limit was 2000, but in open channel flow it is 500. Then flow could also be classified with respect to space, and if we do so, flow could be uniform flow or non-uniform flow. And if it is a uniform flow, then depth of flow remains constant along the channel. So, flow with a constant discharge in a channel of constant geometrical shape and slope, that is an example of uniform flow. So, if you have a channel, and if this is the channel bed, and if the flow is taking place. So, uniform flow means the depth here, and if here if we measure depth, then if this is y 1 and this is y 2, then y 1 will be equal to y 2. So, that means with respect to space, the depth of flow will remain constant, provided discharge is constant, channel's shape and slope is constant. So, if channel shape and slope is constant and flow is constant, then it will produce uniform depth throughout the length of the channel. On the other hand, if it is a non-uniform flow, then depth of flow changes along the channel. So, if it is a non-uniform flow, even with a constant discharge in a channel of varying geometrically shape or slope. So, something has to happen for flow to become non-uniform. So, that could be by change in slope of the channel or by putting some kind of structure in the channel, flow could get converted into non-uniform flow. But basically, if with respect to space, the depth of flow remains constant in a channel, that is referred to as uniform flow, and if the depth changes, then it is referred as non-uniform flow. Similarly, flow can also be classified with respect to time. So, with respect to time, the flow is referred to as or classified as a steady flow and unsteady flow. So, a steady flow means the depth of flow does not change with time at a location in the channel. So, if in this case if we draw a channel and if flow is taking place in this. So, this is your channel bed and this is the water surface. So, if you consider a particular location and if measure the depth of water, so over a period of time there will be no change in the depth of flow. So, with respect to time at a particular location, the depth of flow does not change. So, that is steady flow, whereas if depth of flow changes with time at a location, then it is referred to as unsteady flow. If it is a flow of this kind of or if a particular place after some time, if flow is having a different depth, then it is referred to as unsteady flow. So, with respect to time it is steady flow or unsteady flow, with respect to space it was uniform flow, non-uniform flow, with particle motion it was laminar flow or turbulent flow. So, different possible classifications of flow is possible. So, continuing with the flow classification. So, if we combine these terms which we have just seen, the flow could be steady uniform flow, that is there is a constant depth in time and distance. So, if you take a flow case where the flow depth does not change with the space, and if you take a particular location it does not change with time, then it is referred to as steady uniform flow. On the other hand, we have other classification as steady non-uniform flow, where depth varies with distance, but not time. So, if you consider here, so if there is some kind of a obstruction in the flow, because of that the depth will change with the space, but if you take a particular section and if you measure the flow with time, the flow remaining constant, the depth will remain constant. So, that kind of flow is referred to as steady non-uniform. So, with time it is steady, but its phase is changing. So, it is that is why it is non-uniform. Then there is a other case of unsteady flow, where depth varies with both time and distance. So, if depth flow varies both with time and distance, then it is referred to as unsteady flow. And there is a theoretical possibility of unsteady uniform flow, but typically this is not possible, that with time flow changes, but with distance it does not change, that is very rare. So, it is typically we only talk about unsteady flow. Then we can come to another kind of classification, that is non-uniform flow. Within non-uniform flow, flow could be further classified as gradually varied flow or rapidly varied flow. So, when the velocity and depth of flow change over a long distance in a channel, that is referred to as gradually varied flow, wherein if velocity and depth of flow change over a short distance, then it is referred to as rapidly varied flow. And the different types of flow may occur in the same channel. So, if it is same channel which is subject to different kind of conditions, then the flow may change from one place to the other and the type of flow may be different. For example, if it is a sluice gate, so immediately after sluice gate there will be a case of rapidly varied flow, that is the flow depth will change rapidly over a short distance of, and after that it might take a form of uniform flow. And then if there is some obstruction, a weir is placed, then suddenly the flow, because of hydraulic jump phenomena, the rapidly varied flow will occur, and then for some distance there might be uniform flow. When there is some sudden fall, then rapidly varied flow. Then after that there is nothing happening much, then it could be gradually varied flow. Then further if slope changes suddenly, then it could be rapidly varied flow, and finally it could further finally uniform flow. So, depending upon the conditions within the channel, whether the slope is changing or depth is changing or some structures are put in the same channel over a certain length, different types of flow could be seen. So, steady uniform flow in channel, if you consider in open channels, then basically we know that steady uniform flow, that is the depth of flow does not change with time or with the space, that is the steady uniform flow. So, in this case streamlines are straight and parallel, that means streamlines will be followed. Hydrostatic pressure distribution will be uniform, that is here the uniform hydrostatic pressure will there, and velocity head will be constant. So, this is velocity head v square by 2 g, this is the difference, this is velocity head v square by 2 g, that will remain constant throughout. So, channel bottom, which is here, the water surface, that is this line water surface, which is also referred to as hydraulic grade line or HGL, and energy grade line, that is EGL, these are all parallel. So, here these are 3 parallel lines are there, and if flow is steady uniform, then continuity equation and Manning's equations are applied, and we have already had a lot of examples solved dealing with steady uniform flow. Whatever cases we discussed under vegetative waterway, they were all considered as cases of steady uniform flow. So, in the open channel. So, that we have already a lot of experience with. Then we come to the next, that is steady non-uniform flow in open channels. And if you look at the energy relations for steady non-uniform flow, and if this is a channel, and if we consider 2 sections delta x distance apart, that is this is section 1 and this is section 2, this is 1 and this is section 2, which are delta x difference apart in a channel, then the one dimensional energy equation may be written as, that is at section 1, the sum of the energies, that is pressure, velocity and elevation, that is pressure head, velocity head and elevation, sum of that will be equal to the pressure head, the velocity head and the elevation head at section 2 plus the HL, that is head loss due to friction. So, this is the form of one dimensional energy equation for steady non-uniform flow. Now, from figure we can see that P 1 by gamma plus Z 1 is equal to y 1 plus S 0 delta x, that is at section 1. If you consider this section we see, then Z 1 plus P 1 by gamma is y 1, that is the depth of flow, and this is the elevation change because of the bed slope. So, bed slope is S 0, which we have seen in previous figure. So, S 0 is bed slope and the distance between 2 sections is delta x. So, this elevation is from the datum, it is S 0 delta x. So, that is why P 1 by gamma plus Z 1 is y 1 plus S 0 delta x. Similarly, at section 2 if you see P 2 by gamma plus P 2 by gamma plus Z 2 is y 2, and this is what it is. And S 0 is the slope of the channel bottom and y is the depth of flow that we have already seen. So, if we consider energy coefficients alpha 1 and alpha 2 is equal to 1, then equation 1, the previous equation, we are simply replacing the pressure head and elevation heads summation by these considerations in terms of depth and slope. So, that is what it is. So, y 1 v 1 square by 2 g plus S 0 delta x is equal to y 2 plus v square by 2 g plus H L. So, basically this has come in place of this and this has come in place of this from equation number 1. So, if we consider a special case where channel bottom is horizontal, that is S 0 is 0 and head loss is 0, H L is equal to 0, then equation 2 becomes y 1 plus v square by 2 g. We remember we had S 0 x delta x, so S 0 is 0, so that term is gone, and on right hand side we have y square plus v square by 2 g, and we are assuming HL is equal to 0. So, the HL is gone. So, this is what we get as equation number 3. Now, at the same time the sum of the depth of flow and velocity head is defined as specific energy, that is specific energy is y plus v square by 2 g, that is the definition of specific energy. So, that simply means that equation 3, that this equation states, because this is nothing but y plus v 1 square y 1 plus v square by 2 g, that is specific energy at section 1, and this is specific energy at section 2, and this equation says that specific energy of section 1 is same as specific energy of section 2. That means, equation 3 states that specific energy at section 1 is equal to specific energy at section 2. And from continuity equation we know A 1 V 1 equal to A 2 V 2 equal to Q. So, we can also write that equation, that is you can replace V by Q by A. So, we can write this equation as y 1 plus q square by 2 g A 1 square and y 2 plus q square by 2 g A 2 square, and A depends on y because A has y, be it any kind of cross section. So, specific energy is solely a function of depth at each section. So, from this equation it is a function of depth only, because A is also a function of depth and depth is already there. So, we can make a specific energy plot. So, for a given channel and given Q, its depth of flow is plotted against E, then we get specific energy curve. So, y is plotted against E and the curve we get is referred to as specific energy curve. Now, you can see that this line, dotted line, represents is 1:1 slope line. So, you just notice that there is a typical shape of this specific energy curve and specific location also, and that is because at 1:1 line E is equal to I. So, everywhere in this, on this line if you see E is equal to I. So, be it here, anywhere, and since E is greater than y, because it has a velocity head also. So, E is y equals to v square by 2 g. So, due to velocity head E is always be greater than y. That simply means that specific converging curve will always be below 1:1 line, because on x axis E will always be greater than y. So, that is why it will always lie below this 1:1 line. This is a very important point you should always remember, because you should never make a mistake of drawing a specific energy curve if somebody asks you to draw over this 1:1 line. So, this is one important fact about the specific energy curve. Now, we see here from this curve that for a given specific energy, if you just draw a vertical line here, this vertical line if you consider, then for a given specific energy, depth could be either large, that is there are two depths possible, this is y 1 and this is y 2, two depths are possible for same energy. And for y 1, when the depth of flow is more, the potential energy is high, and for y 2, when the depth is less, kinetic energy is high. And this y 1 and y 2, where at two depths where the specific energy is the same, they are referred to as alternate depths. So, y 1 and y 2 here, where the specific energy is the same, then they are referred as alternate depths. So, it can be seen that on specific energy curve, a point 4, that is this point is reached where the specific energy is minimum and only a single depth occurs. So, at this point specific energy is minimum, as you can see here, just a single depth occurs, that is y c, and this depth is referred to as critical depth. So, because the typical shape, there is a point is reached where just energy is minimum and there is only one depth possible, and that depth is referred to as critical depth. And at this point, that is where this critical depth occurs, flow is termed as critical. So, this point flow is critical flow, and critical flow is the flow that occurs when the specific energy is minimum for a given discharge. So, that is a typical definition, that critical flow is the flow that occurs when the specific energy is minimum for a given discharge. So, this is the definition of critical flow, and this is very important in flow regime, because a lot of developments depend on this critical flow identification, and we will see this in later parts of lecture. And the flow with which the depth is less than critical, that is velocity is greater than critical, it is termed as supercritical. So, this is depth, critical depth, and below this the depth will be less than critical depth, and that means velocity will be greater than velocity, critical velocity, and that is why the flow is referred to as supercritical flow. On the other hand, the flow for which the depth is more than critical, that is any point above here, then where velocity is less than critical, that it is termed as subcritical flow. So, that is why this identification of critical flow helps us in identifying the flow regime or dividing flow regime into 3 distinct phases, that is critical flow, subcritical flow and supercritical flow. And if we see the characteristics of critical flow, that critical flow occurs when the specific energy is minimum, we know that. So, for a given q, we know that E equals to y plus q square by 2 g a square. So, if we solve for d by dy equal to 0 and set dy by dy equal to 0, then we can determine the depth for this condition, that is for critical flow condition. So, if we do that d by dy, so this is 1, and of course, we have already said that a is a function of y. So, that is why we are also differentiating with this a. So, if we do that, we get q square g a cube dA by dy, that is equation number 8. So, if the T is the width of the channel at the water surface, then dA is T dy, that is obvious, and putting this in equation 8 and setting dy equal to 0 for critical condition, if we do that, we will get this q square T c, we are calling it T c because that is a critical, we are saying, because it is a critical condition, and g a c cube equal to 1. So, this is the condition which we get q square T c by g a c cube equal to 1, and this equation itself can be written in several other forms, like for example, A c by T c equal to q square by g a c square, or A c by T c is V c square by g. So, if the channel is rectangular cross section, then A c by T c is equal to critical depth y c, which is quite obvious because we know that for a rectangular section. So, it will be this is B equal to T and this is y. So, area by area equal to B y or T y. So, that means A by T equal to y. So, that is where, so A is equal to critical depth. So, if we also define q, small q is discharge per unit width of the channel, or capital Q by B for rectangular channel B equal to T c, then we can also write y c equal to q square by g y c square, or y c is cube root of q square by g. So, critical depth for a rectangular channel can be found out provided we know the discharge per unit width, and obviously gravitational acceleration due to gravity g will be known to us. Further, if you apply equation 11 to a rectangular channel, then we also can write y c is equal to V c square by g, or V c square by g y c equal to 1, or if you take square root of that. So, we can write that V c by square root of g y c equal to 1, and this term, that is left hand side of equation 13, is referred to as Froude number F, which is the ratio of stream velocity inertial force to wave velocity gravity force. So, this is a critical flow condition. So, at critical flow Froude number is 1, and for subcritical flow, when velocity will be less than V c, Froude number will be less than 1. For supercritical flow, when velocity will be greater than V c, then it will be greater than 1. So, this is an important finding, and Froude number is used to classify or identify the flow regimes, that is whether the flow is critical, supercritical or subcritical, that is specific energy. With respect to specific energy also, we have already seen this. And there are many practical applications of specific energy constraint. So, we already have seen that Froude number helps in identifying type of flow or flow regime, and critical flow concept is useful in measurement of flow in the open channels. Large number of flumes and broadcasted vias are based on critical flow concept. That is, if you consider the broadcaster via, we typically provide a hump in the channel bed, and because of that what happens, the flow will become for subcritical, because depth will larger depth will be there, and then on the other side it is a free fall. So, from subcritical to supercritical it goes, and because of that there will be some critical flow depth formation on the channel, on the hump itself, and that facilitates measurement of or the discharge measurement by just a single measurement on upstream side. That is the concept on which the broadcasted vias work, which works on the function of specific energy concept. Similarly, the critical flow typically occurs whenever there is a slope changes in a channel. So, wherever slope changes, the flow changes from subcritical to supercritical, and or otherwise. So, because of that there will be critical flow, or if there is a free overfall at the end of channel. So, if a long channel is there, suddenly there is a free overfall, then at the end of the channel there will be critical flow. It is critical flow concept is useful in handling smooth channel transition problems. So, how to, if it is there is a change in slope or change in bed width, then how the slope will change and how transition should take place, that is found out through using this critical flow concept, and also by computing water surface profiles. So, channel transition already we have seen could be due to gradual change in channel bottom or in channel width, both the cases there will be channel transition. So, if you look at example number 1, then it says determine the critical depth in a trapezoidal channel for a discharge of 14 cubic. The width of the channel bottom is 6 meter and the side slope upward at an angle of 45 degrees. So, we have been given data given are q equals to 14 cubic, b equals to 6 meters and z is 1, because 45 degrees nothing but 1:1 slope. So, this is the condition we have already seen, that is q square T C by G A C cube equal to 1, that is specific energy condition, and from here A C cube by T C is q square by G. So, q is known, G is known. So, that value comes out to be 19.98. And for a trapezoidal channel, we know that if we are talking about critical condition, because this is a critical condition we are talking about. So, if depth, you consider that depth is critical, so area is critical. So, critical area is b y c plus z y c square, b is given as 6 and z is given as 1. So, that means A C becomes 6 y c plus y c square and T C is b plus 2 z y or 6 plus 2 y c. So, if we put the values in the previous found relationship. So, 6 y c plus y c square is cube divided by 6 plus 2 y c, and that is equal to 19.98, and that means it is only a function, this equation is a function of y c. So, by trial and error we can find out, and we will find the value of y c, which comes out to be 0.78 meters. So, the critical depth for the given condition in this channel is 0.78 meters. So, we take another example, a rectangular channel lined with planed wood n equals to 0.012 has a width of 8.2 meters. When the depth of water is 1 meter, the flow is 10.5 cumecs. Determine the required slope, the specific energy and the type of flow. These three things we have to find out. So, data given are rectangular given b is equal to 8.2 meters, rectangular channel of course, y is given as 1 meter, that is depth of water, q is given as 10.5 cumecs, and for wood planed the value of Manning's roughness coefficient n is given as 0.012. Let us say that channel bed slope is S. So, cross sectional area of the channel is b times y, and b is known, y is known. So, it is 8.2 square meters. Wetted perimeter B plus 2 y, B is known, y is known. So, it is 10.2 meters. Hydraulic radius is ratio of A by P. So, A by P is 8 by 2 by 10 by 2 is 0.8 meters. So, from continuity equation V equals to Q by A. So, Q is known, A is known. So, V comes out to be 1.28 meters per second, and Manning's equation we know V equals to 1 by n r to the power 2 by 3 s to the power half. So, V is known, n is known, r we have already calculated. So, only unknown is s. So, from here we can find which comes out to be s equals to 1:3140 watts. So, that is the bed slope of the channel, that is there will be 1 meter fall over 3148 meters horizontal. Now, specific energy can be calculated using the base equation, that is y equals to V equals to y plus V square by 2 g. So, y is known here, V is known here, g is known here. By putting the values we get specific energy value is 1.08 meters. And then third thing we have to find out the Froude number. The equation we already know, Froude number is V by root g y. And so, V is known here, y is known here, g is known here. So, if you put the values we get the value of Froude number is 0.41, and if you remember that if Froude number is less than 1, then the flow is subcritical. That we just saw, we saw that for critical flow F is equal to 1, and for subcritical is less than 1, for supercritical is greater than 1. So, since it is here 0.41, so flow is subcritical. So, the three answers we have, that slope is 1:3148, energy is specific energy 1.08 meters, and Froude number is 0.41, and flow is subcritical. So, with this we have seen some of the fundamentals of open channel hydraulics, specific energy concept, what could be possible application, and we will continue with further fundamentals of open channel hydraulics in the next lecture when we commence. Thank you very much.